Alright, I plan on recording with my cell phone placed above my desk at home the steps on solving problem 45 with some additions in your textbook. This is page 134. So problem 45 on chapter 3, and this is a cylindrical shaft of constant diameter, and there's a bevel gear, and these are the reactions at the meshing, where the gear meshes with its conjugate gear with a pinion possibly. And this appears to be another it will be a straight spur gear, or maybe a pulley. In case of a pulley, the belt would be stretched down, and there's a second pulley, of course, is driving the shaft, or it's driven. We don't know. So what do we want to do? It's here on the bottom that says for problem 39 to 50 to draw free body diagrams and then produce the shear force bending moment diagram. I'm also going to look with you at the deflection of the shaft at two locations, at the bevel gear and at the pulley. Okay, so something's wrong. I was trying to get the no. Alright, so I'm also having my desktop computer. It's the first time I'm doing this. Open the PDF to where I can see the text of the problem, but and I have some markings here to where maybe this way. Okay, so let's do the drawings of the shaft, and so we're having I'm not going to repeat the figure in the book. We have some notation. So this is this is where the bevel gear is. It's 11 and 12 from the other support. This support at C will be point B. This is the support at C. Okay. Support at A. And then we have the 120 pound from the pulley. Okay. So point A, B, I have C, it's a D. And because I'm dealing just with the shaft, the effect of the 180, the horizontal force, would be, so this is going to be the 460 pound force. Then I have an axial load that is 180 pounds. And I also have a moment. So moving the two forces, the vertical force is a sliding vector. It's moving it anywhere along its line of sliding does not change the effect. But if I move on the axis the 180 pound force, then I need to account for its effect. Yeah, my computer just froze for some reason. I opened too many PDF files. Okay. All right. So the moment here at B, it's going to be the moment M is going to be 180 times 6.75. And that is going to be 180 times 6.75. That's going to be 1250 we're at a 15. And I have a better marker. These are pound inch. Okay. We know we know some distances. There is the 11 inch, and then there's this distance. And I'm going to restart my desktop computer. Come on. And then we have 5.5 inches. This distance being 12 inch. Okay. So what is going to be the reactions of the supports? A reaction at A and a reaction at C. Well, for that we need to sum moments about point A to calculate reaction at C. Also, it says choose which bearing of the two is going to take the axial load, and I'm assuming A to be that one. So I know reaction at A in the horizontal direction is going to be 180 pounds. Clearly sum of forces in the y direction. And further looking for markers. So, come on, I'm trying to restart my desktop computer. Okay, so sum of moments about point A equals 0. So what do we have? We have and positive for moments, I'm going to assume to be for moment equation, I'm going to assume to be counterclockwise. Okay, so there's going to be 460 negative times 11. Okay, this force and this arm. And then I have the positive moment, 1215. All right. And then I have also negative the 120 force times the entire length of the shaft, which is 11 plus 12 plus 5.5. And that's 28.5. Okay, equals 0. Well, I forgot exactly what I was looking for. Sorry. So should also include plus the RC force multiplied by the 11 plus 12, that's 23. All right, so solve for RC, and that's going to be the whole sum here. So 460 times 11, negative 1215, positive 120 times 28.5, divided by 23. So RC is going to be, I said 28.5 times, I still have on my calculator 28.5, so multiply times 120 plus 460 times 11, negative 1215, and divided by 23. So I have RC 312.869, easily 9, and these are pounds. Okay, so that was for sum of moments in the about A. So I'm summing moments about point C, the same, assuming positive moments to be counterclockwise. So sum of moments about point C, equilibrium, in order to find the reaction at A, this time RA. So I'm having RA times this distance is going to be 11 plus 12, 23. And then I have positive, it is positive, being counterclockwise, 460 times 12 inches, 12 this value. No need to indicate units. And then I also have the moment. It's there, so I have positive 1215. Okay, the moment. And then maybe I should call it moment at B. And then I have a negative moment, caused by the 120-pound force. And this goes so negative because it's counterclockwise, or clockwise rather, opposed to the sign convention here. So 120 times 5.5 equals 0. So one more time. RA times 23, negative, positive, 460 times 12. And I have this moment by itself. And I have this force, 120 times this arm, and negative. So from here, this equation gets me the reaction at A in the y direction, RA, and this is going to be 460 times 12 plus 1215 minus 120 times 5.5, everything over 23. Okay, so 460 times 12 plus 1215 minus 120 times 5.5 equals over 23 equals RA is 264.1 pounds. 9 and 1, it's encouraging. Looks like when we are going to sum for verification, so check. I'm summing forces in the y direction. See if it's a 0. So let me further populate the drawing. We've got RA 264.1 pounds. RC was 312.9 pounds. And then summing, let's say positive is up, so I have 264.1 plus 312.9 negative 460 negative 120. Let's see if this is equal to 0. So 264.1 plus 312.9 minus 460 minus 120 equals negative 3, which is almost 0. Maybe because of, let's see again, it should be closer to 0. 226.1 plus 312.9 minus 460 minus 120 equals 3. I hope I haven't missed anything. Anyway, so it's approximately, compared to, the smallest of the 3% error. Okay, so we have reaction forces and the supports, and we can proceed and draw the shear diagram, shear force diagram, the V diagram. So V, and units are pounds, units of force. And it begins with a positive shear force of 264, and then it goes, so this is positive shear. I have a drop by 460, so from 264.1 minus 460, I go to negative 195.9, 195.9. Okay, nothing changes until I get to point C, where the negative 195.9 gets changed by positive 312, so plus 312.9, that's 117, and let's assume it closes to 0. This is positive again. Should have been 117120. I'm still puzzled. Maybe I missed something somewhere. Maybe a 5. You know, one of these forces. Okay, maybe you can figure out where the small mistake originates from. I'm sorry for this. Okay, so the next after shear diagram, shear force diagram, is the bending moment diagram, and we're having zero moment here. I'm looking at this diagram. I have a positive slope, and the positive slope is 264.1, and here, because the 0 on the V diagram, I'm expecting a maximum, but it's not a smooth maximum, rather a cusp on the diagram. So again, moment in units are pound inch. And what's the magnitude of this moment? Is going to be the area principal, so the area of this rectangle, 264.1, that is, times 11, it's 2,905.1, so 2,905.1. Slope changes, and it's going to go negative 195.9, and I'll have another minimum. So let's see what the balance of moments are. To the current moment, oh, and by the way, let's not forget, there is a concentrated moment. And this concentrated moment, there is the what page is it? 107. It says, when a concentrating bending moment acts on a beam in a counterclockwise direction, the moment diagram drops. So there will be a drop by 1215, like right here. Immediately after B, I have a drop. So the moment acts counterclockwise, and I have a drop in moment. So 2905.1 minus 1215, and this is 1,690. Again, this was for the entire one. I have a drop to only, so this piece here, it's 1690.1, and then I have a going to the other, you know, these are in alignment. So how big is this moment? Let's calculate it. Again, this piece here, it's equal to MB, that is 1215. All right, so the current value 1690.1, and then area method, I'm to that positive value, I'm subtracting so negative 195 5.9 times 12, and that's 660.7, negative 660.7 poundage. Okay, and here's where the slope, so this was a positive moment, this is a negative moment, and it should go to 0 because the end of the beam is free. If we take the product, I said 117, this should be, so instead of 117 should be 120, somewhere here, round off air or something. This is not exactly 0. So if we take 117 and times 5.5, I get 643.5. If instead, I take 120 and times 5.5, I get 660. So, all right, so this is also equal to, again, applying the area method from right to left. This is 120 times 5.5. Okay. All right, so we have the diagram. We have the maximum values of the moment. Remember the concentrated moment here. It's causing a drop, a reduction in the moment right to where the moment is applied. And what I also did, in addition to what the problem stated to find these diagrams, I said let's assume the diameter to be 1 inch. So shaft diameter 1 inch. Again, this is problem 45. So problem P345. Those of you who came late to this recording. All right, so I assume shaft diameter to be 1 inch and to be steel, carbon steel. So carbon steel, if you go to the back of the book, we have materials properties. So I'm on page carbon alloy steel. I'm on page 787. If you turn to 788, it says modulus of elasticity for most carbon steels is 30 times 10 to the power 6. So E is 30 times 10 to the power 6 psi. I've got this from, so it's page, let's see how well it's, yeah, page is 788 of your book. Okay, so what we want to do is to calculate the maximum stresses, and I have compression, so I could draw a axial force diagram right below. So, and I have compressive force negative 180, so axial force 180 pounds negative between A and B, nothing elsewhere. So there will be, and transition happens right here where I have a lot of things going on. Theory says that flexure formula occurs or applies correctly away from where the loads are placed, but we constantly ignore that, and we just because maximum of moments occur where the forces are. So really here's where the key going on the shaft is very well likely to be present, and then may have splines and other effects. All right, so let's draw the so we have a positive moment. We go with the maximum value, and that means that I have compressive stress on above, tensile stress below. Again, shaft is around 1 inch. 1 inch. And I'm going to calculate the sigma due to bending. Sigma max. And this is at point B. And remember, tensile stresses are worse than compressive stresses, so I'm going to use the M. It will be M at a maximum at point B, but not MB the way I had it. Okay, so MB is the external moment at B, although here we're talking about the maximum moment on the diagram. Okay, so it would be M. C is diameter over 2 over polar moment of inertia of a round solid, pi diameter at power 4 over 32. We're using the section modulus. It will be M over pi diameter at power 3 over 32. Now this is without the compressive stress effect of this axial force. So let's also consider that then. So I'm going to just say, include negative would be axial force. Never label it, so simply say 180 pounds negative because it's compressive stress added to a positive tensile stress. 180 divided by area, pi diameter of the shaft square over 4. Move it here, so 180 divided pi diameter squared over 4. So what do we have? I'm looking at the diagram. 2,905.1, 905.1 over pi 1 inch power 4 over 32, negative 180 over pi 1 squared over 4. Okay. Let's calculate this first, and then this one, and if I take them positive with a negative, it gives me the maximum positive moment, and then if I take it the other way, negative and negative, it gives me the maximum compressive stress. Okay, so sigma max tensile and sigma max compressive. Let's see their value. So 2905.1 over pi times 32 equals, just this piece, 29591.1, and then this other piece, 180 over pi times 4, that's 229.2. Okay, and this was negative, so maximum tensile will be this value, negative this one. right, 2959.1 minus 229.2 equals 2,930, no, rather 293, whatever, 61.9. And these are, we used pound and inch, so this will be PSI or 29 KSI. And then for compressive stress, it will be a negative. I have 29591.1 negative the same number. I have negative 29361.9 psi. Okay. Tensile stresses have more damaging effect than compressive stresses. The shaft is rotating though, so we're having the case of will be the case of fatigue loading, and that will be discussed in the next chapter. Okay. So yet again, the text of the problem. Let's also look at deflections now. It's not part of this. It's not the way, not even calculating stresses. Where is this coming from? Let me represent the. So we have the shaft at B. So the shaft. I made a cut, and I'm inspecting what's left of the shaft from A to B. And we have the compressive stress above and tensile below. Okay, so compressive and tensile. And to this, I'm adding the compressive stress caused by, so it points towards the section, it's a compressive stress. So this, it's added to this, in this, it's subtracted from this. The result is an increased compression and a decreased tension. The zero stress at neutral axis is going to be moved below, so, oh, rather, I'm sorry, so compression and tension, is this being this number 29361.9 I said, and this one is negative 29361.9 psi and psi. Okay. All right. So calculating the maximum stresses. Let's now look at the deflection I said. So page and yeah, maybe I should redraw the, this is the loading. So I have the diagram, reaction, force, another force. This is 460. We're going to ignore the axial load, although that has an effect in reality. And then I have the moment, the 1215. Okay, you know these 264.1, 312.9, 11 inches, 12 inches, and 5.5 inches. Okay, so let's see what the deflections are at the two forces. And back of the book has deflection cases. Let me go take you there. So beam deflection formula simply supported beams. Okay, and this is a particular case where the load is right in the middle. We have this case where it's off the middle, and then so I have principal superposition. This case overlapped with this case, and then I have, so it would be an overlap of this case, and this case. I'm on page 801, and so again, principal superpositions. I need deflection at B for the three cases. At B where the moment is, and then at the point equal to something when I have this third instance. All right, so let's take it. Does it have a case? Yes. So overlap of, I'm writing here, see page 801. There's an overlap of B plus, I hope you follow from your own textbooks. You don't watch it like a movie, what I'm doing here. So plus case F with a concentrated moment plus case G as in George. Okay, so case B only. I could work it this way. Let's see. So case B. Y at B with P only. So that's going to be, I have the equation. P, this is my load, P for 160, so I have negative 460 multiplied by, that's going to be the distance A, and that's 11 inches, squared times distance B, which is 12 inches, also squared, over 3. E, we said this is a steel material, carbon steel, 30 times 10 to the power 6. Power 6 times, I have I, moment of inertia of a round solid. So I pi diameter power 4 is 64. Let's calculate it. I pi diameter power 4 over 64. Lucky is what? 1 at power 4 is 1. So pi over 64. This is 0.04908709. I put this in the memory of the calculator. So times, we said 0.04909, and then times length L. So length of the, between the two supports, which is 11 plus 12, that's 23. Okay, so let's see what this number is. 460 times 11 squared times 12 squared over 3 over 30 exponent 6 over, have it in the memory, over 23 equals and it's negative 0.788 okay, inches. And again, these were inches power 4. So that was deflection at B caused just by the 460 force, pound force. We look at case F now. So I have case F, and I have deflection where the moment is concentrated moment at M. Actually, there is no deflection there, so that's a good news. The case of a deflection of this point, how do we capture that? Because it's outside of the support. All right, so y at B in case F moment only is 0, right? Obviously. But if you want deflection somewhere outside of the beam, it says between B and C, we're going to have to expand this, apply this equation with a x value that is bigger than L to get deflection outside of C. It is x equals L plus our 5.5 inches offset. Okay, and then we have the case G, and I have y at B caused by just the cantilever, and this is, let's see, so I'm looking at a force, down force, and I want to calculate x. It's definitely left of the support, my case here, so I match A and I match this, and I have deflection at 11 inches from A caused by this force alone. And at the end of overhang, I should have read this carefully. So there's no equation that gives us deflection anywhere along the beam. What a shame. So how can you go about that? I believe the strength book may have more detailed equations. So end of overhang, maximum deflection here. Let's see, if I take so 11 plus 12, that's 23 times 0.577, that's 13. It doesn't help. I was hoping that 0.577 times full length is going to give us yeah, what a shame. So there's no equation for this type of loading that gives me the deflection at any point x. Elsewhere in other sources, maybe I'm at home, I don't have my strength book to verify there, and maybe it could be on the internet. I mean, oh, took a pause, my my desktop computer. Let's see. So I'm looking at deflection formula. I want to leave it. Let's see how many minutes of recording. 44 minutes. So let's look at deflection equations. Deflection equations of beams. I hope we'll find something. Mechanical structure beam, deflection, stress formulas, engineering edge. All right. So maybe if what is the deflection equations of beams? Let's go to Wikipedia. Mechanics of materials. Beam deflection tables. Okay, maybe here. So I have beam deflection table. Not even. I should have read carefully. You know, I expanded the problem of what's in the book. I knew the process, didn't realize that there's no equation available to calculate deflection at any point caused by an overhang. Beam deflection formula, Iowa State. Okay, so let's see. If I rotate the view, so cantilever, force between supports. Oh, maybe I found it. So I'm going to solve another problem from this chapter 3, problem 48. The text of the problem says that we have to draw a free body diagram of the main shaft portion. And so main shaft portion. It's assumed that the torque is resisted by the bearing at C. So for this portion ABC of the shaft, we need to draw a shearing force and bending moment diagram in the, will be the case of the vertical plane, that is YZ plane. And then I also need to draw a torque diagram of the shaft as along the ABC line. Okay. So what I did, I made a photocopy just of the the drawing for this problem, and let's see how we're going to solve it. So we have two forces, and they are different. There's not a couple, they differ in magnitude. So starting with this 200-pound force, if I am to assume it being at so moved along this 4-inch long section here, and I'm using red color, then I need to account for this. So remove it here, move it here, is the same 200 pounds, but I need to include a moment along the x-axis. Would be, in the magnitude of it will be 200 times 4, that's 800 pound-inch. Looks like I need to retire this red color. Doing the same with the 600-pound force, I take it from here and move it here. So 600. I need to account for this shift by a moment that is 600 times 4. It happens that this distance equals this distance. 600 times 4, that is 2,400 pound-inch. Okay, so this was first move, and then if I take the force from here, the 200-pound force, and move it at B, so 200, then I need to account for this displacement along the x-axis by introducing a torque about the z-axis, and this torque, it's going to be equal to 200 times 8, which is 1600. So 1600. Taking the 600 pound force and moving it on the z-axis, it would require to add a torque that is about the z-axis, and the direction of rotation, it's actually the same as the 1600 pound-inch force. So I have another torque, and this is, we said 600 times 8. That's 4,800 pound-inch. Okay, so the ABC bar with simple supports at A and C, and drawing it on in two-dimensional view, not perspective view, will look like this. So I have the bar, and I have the support here. Let me show this as a sliding support, and this one, and it's point A, and at point C, I have the fixed support. There is 12 inches, and then I have, so remember this was 600, I should have labeled it. So the 600 down force was moved here, and I had to introduce the torsion. Okay, so there will be a down force, resultant down force of 600 minus 200, that's 400 pounds. And then I had these two torques are in the same direction, the 800 pound and the 2400 pound. So they are going to be added together. So it's 3,200 pound-inch. And this is a moment about the x-axis. And then I have a twisting of this portion of the shaft, torque loaded by what torque would be the 1600 and 4800 together. So 16 plus 48, this is equal to 6,400 pound-inch. And it what direction? So it will be the way it's shown. So it's in the positive axis of z. I can represent. So the torque load on the torque, and it's in the z direction. This will be a moment that causes bending, so it will be an M bending moment, and it's at point B on the beam. Okay, so this is our new problem, and we need to draw the shear force and bending moment diagram as well as the twisting diagram. I'm going to do the twisting diagram first, and we can use bars like boxes or similarly to distributed forces. So the torque load, and it's positive because it tends to turn the twist the beam in the positive or z direction, so it's positive. And the magnitude is this one. So torque problem solved. Let's look at I went to get a better red color Sharpie. So what we need to do is to calculate the reactions at A and the reactions at, so I have RA and the reaction at C. Okay, it's going to be only the 400-pound force in this moment are going to determine the magnitudes as well as the possible orientation of these reactions. It might be RA that is the opposite, we'll see. So to calculate reaction at C, I'm going to sum forces, rather moments, sum of moments about A. Sum of moment about A, we have equilibrium equals 0, so that translates into, and by the way, positive for moments on this moment summation. It's assumed to be positive, so it's assumed to be counterclockwise, as we did before. So what do we have? We have a negative moment, which is 400 force times 12-inch arm of the force. And then I have negative the moment at B, 3200, and I have positive RC times the full length, which is should have written this, so it's 16 inches. So this one is 16 inches. So 12 plus 16, that's 28. 28 equals 0. So I get for RC, it will be, so this group negative goes to the other side, turn positive, so RC is going to be a positive value. It's going to be 400 times 12 plus 3200 times by itself, it's a moment, divided by 28. So what do we have? 400 times 12 plus 3200 equals over 28 equals, this is 285.7 pounds. We'll repeat the analysis for summing moments, that is about point C. So I have sum of moments about C equals 0, and the same positive counterclockwise. So what do I have? I have a negative moment RA times the full length of the beam, which is 28, and then I have negative, or rather positive, the 400-pound creates a positive moment, this sign convention here. So positive 400 times 16, and then I have the negative 3200 equals 0. So RA, reaction of A, this is going to be this group 400 times 16 minus 3200 over 28, and the value is 400 times 16 minus 3200 equals over 28 equals, that's 104.3 pounds. Let's check. So I'm going to put the actual value. So both positive, it means that we've got the orientation of these forces right. So first one, RA is 114.3 pounds, and then RC, we got it early, it's 285.7 pounds. Okay, so verification. Assume positive goes up, it's 114.3 plus 285.7, and then negative 400. Is this equal 0? So 114.3 plus 285.7 minus 400, exactly 0. So it's correct. We can now invest in drawing the shearing force and bending moment diagrams. I'm going to align my my diagram with the figure like so, and for the V diagram, the units are pound. We have again positive, it's up, so I have 114.3 and stays the same, and then I have a drop by 400, and then it goes to negative, so I have positive and negative. This is 400, and this is going to be negative 285.7 immediately right after, or a C as we move to the right, it drops to 0 by adding this positive value. Okay, so V diagram. The moment diagram, and units are pound inch. It goes like so. So I have a positive slope of 104.3, and we're expecting a maximum with a cusp, or maximum at this location at B. And what is the maximum, or the moment at B? Is going to be this area. So 114.3 times 12. So moment, bending moment at B, area, principal 114.3 times 12. That's 1,371.6 pound inch. And then it goes to 0. No, mistake. I have the bending moment, the concentrated moment, and so we know that the concentrated moment, there's the sign convention. Going back to the pages where it's the sign convention for moments is listed. So when a concentrated bending moment acts on a beam in counterclockwise direction, ours clockwise direction, the moment diagram rises. So again, the moment is clockwise, and it's going to add this value to the diagram. So, and it makes sense because I'm continuing with a negative slope, which is bigger than this one, and close diagram to 0. Right, so this piece here, it's equal to the concentrated moment, 3,200 pound-inch. This entire piece now is going to be 1,371.6 plus this piece, 3,200, so plus 3,200 equals, so the maximum bending moment, it happens at B, and it's 4,571.6 pound-inch. It should be also equal to the area of this triangle taken with the negative with changed sign, because we go from right to left. So if I take 285.7 and multiply it by 16, I should get, and I do get, the same number. Okay, or very close. 2571.6 versus 2571.2. So both appear to be correct diagrams. We took care of the torque diagram earlier, and this problem is solved. Alright, so out of chapter 3, we're going to solve problem 81 on curve. It's a curve beam problem. And let's see what the text says. So a hanger is made of ASTM A36 structural steel bar with a square cross section 10 by 10 millimeters. As shown, the radius of curvature is 150 millimeter to the inside surface. Determine the load F that would cause yielding of the steel. So I'm starting with making a sketch of the system, and we were having a let's see, looks like the zoom factor is too big, so yes, and I'm going to place 2 markers, 2 marks. Okay, so the problem is 381, and we have that curved beam, so there is an arch of circle, and it extends down straight, the straight portion, and I'm exaggerating the thickness of the bar. I don't care about the hook here, and this is the load F, which I want to find, and this is assumed to be a ground connection, and we're given this distance from the wall where the hook is attached to where the force is, and then we're also having the radius, the inside radius specified is 150 millimeter. Bar is 10 by 10 millimeters, and the material is ASTM A36 structural steel. So let's first see what the yield strength of this ASTM steel is. I'm looking the appendix is Appendix 7, Properties of Structural Steel. And what do we read here? Carbon steel shapes, plates, and bars. And we're looking for the megapascal. This is ultimate. Yield strength is 248 megapascals, 48 megapascals. Okay. We're going to implement the equations that we learned for curved beams, but before that we need to determine or decide where the maximum bending it's going to happen, and that was going to be like right here where the straight portion turns into an arch. Why is that? Because I have the maximum arm to the force F. And I didn't finish the drawing, so 325 millimeters. And the moment, the bending moment, M, is going to be a negative moment because it has a tendency to further bend the beam. And you calculate it as, or measuring the distance to the neutral axis, or rather the centroidal axis. In this distance, it's going to be from where the force, the line of action of the force, to the centroidal axis. This distance is going to be 325 minus half of this distance, which is 10 millimeters. Okay, so 320 millimeters. That's the arm of the force. So the moment is going to be 320 times F. Again, F, it's not known at this stage. And the value is, nothing to calculate. So yeah, we have figured out what the moment is with as function of F. We're going to experience two effects and want to consider both of them. Makes the problem a little bit more complicated, but we capture both effects, which would be this cross section. It's going to be, on one hand, the parabolic stress distribution according to figure 324, and here the moment it's inwards, so this is a mirrored image with tension on top, compression below. Okay, and then to it I'm going to add, so let's see, if I'm in a rotated view to match the figure 324, but mirrored to where I have tension on top. And compression, so tension on top and compression below. And to this I said we're going to add a compressive stress caused by the, and if I'm to do a free body diagram of this section where the curvature starts of the beam or of this support, and I'm looking at it this way now, I'm going to see this force causing direct compression, and because of this offset is going to cause also bending. So free body diagram, this is assumed to have curvature, the beginning of the curvature of the beam. I have a down force F, and I have a moment that goes this way. The pair image, not at scale and not aligned, would be compressive force, and I have this moment. Am I showing the right way? Yes. So force F and moment M and force F. The moment has the tendency, and it's clear from this original figure that I drew, has a tendency to further bend the beam. All right, so I'm coming back to this diagram showing the overlap of effects and beam stress in curved beams, and then on top I have compression. So arrows point towards the cross section. Okay, and it's going to be a slight reduction, or reduction by this amount. This is uniform stress F over area of the section. It will be 10 times 10, 100 millimeters. Okay, so F over A. And then we have sigma on the outside, and then it's sigma to the inside. Okay, so what we're, again, and it's not at scale. This doesn't, you'd expect this to be less compared to the bending stress, but again, this amount will be removed from, because it's compression working against tension, will diminish the amount of tension, and this on this side will increase the amount of compression to the inside of the beam. Okay, so let's see if we're to implement equations 328, 329, we need to calculate the radius. Back to the figure, we need to calculate the radius, capital R, that locate from the center of curvature of the bar, locate the neutral axis. So this is neutral axis, and that's going to be area over area shape factor. So I have R that occurs in equations 328, 329. R is area, we've got to calculate it, over area shape factor for this cross section. What is the area shape factor? For we're looking at the at this figure here, so it's going to be B, 10 in our case, as well as H. B and H are the same and equal 10. So according to this entry on, let's figure 325, I have area shape factor, it's B natural logarithm. So whatever this is, it was explained. I'm not going to redraw this just because the scale is not proper. This should be less stress than it's this one. Okay, so area shape factor is going to be B, we call this B H, so B times natural logarithm outer radius over inner radius. So B on one hand is 10, and then I have natural logarithm of the inner radius and outer radius of the curved B. The inner radius, it's already given in the problem, and knowing the cross section, so inner radius is just R, it says, but that's the inner radius. So inner radius is 150. Outer radius is going to be this radius, or outer, and it's going to be 10. From here to here I have 10 plus 150, it's 160 millimeters. Alright, so 160 over 150. It is 15 over, or the 16 over 15, and then natural logarithm and times 10. So area shape factor, it's 0.645 3854. And it's unitless. It's no, I'm sorry, it's not unitless. It has units of length, so units of millimeter. So from here, with the known area shape factor, I can find R as 100 from above over 0.6454. Okay, so radius from the center of curvature to where the stress, when it's just the bending, the moment considered, not this effect, it's, let's see, over, still have this number, I divide by 100 and take the inverse. Okay, so radius 154.9462 millimeters. I'm looking at the number, it makes sense. So it's a value that goes between 150 and 160, and it's less than their average, which would be to the centroid for this problem. So it's to the inside of the centroidal arch of circle. Okay, so it makes sense. The value makes sense. Okay, so now that I have the moment as function of f, I have the capital R. I need also the centroidal radius, and that's easy to, again, centroidal radius, which occurs in this these two equations, RC is going to be the middle radius, and so RC is going to be the inner radius, to which I'm adding 5, that is half of 10, so 155 millimeter. And I have our the two inner radius, outer radius. Okay, so next I'm going to calculate, it will be function of f, yes, and by the way, there will be the tensile strength that is more severe. Compressive stress is not. So really, we're going to relate or rather set the limit condition where the maximum tensile stress with consideration of the compressive effect of the force going producing direct compression or compression over this cross section, and set it equal to the yield strength of the material. So we're just going to calculate the outer stress using equation 328. So I'm going to implement this equation. Sigma out is going to be, we have it as M, I'm copying the equation from the book, R minus R outer over area of the cross section times outer radius, and then I have the centroidal radius, then minus capital R, that's the radius from the center of curvature to the neutral axis. Okay, so, and then to this, I need to respond. There's student knocking on my door, so a few minutes. I'm recording live. Okay, so with a negative moment here, I need to take this as negative, the way we had it, negative 320 times f. This will end up being a positive value, and then from this one I'm going to subtract F over area, and I'm going to say this is equal to SY. Okay? So, let's see what I have. There is negative 320 times F, and I have capital R was 154.9462 minus outer radius 160, and then over area, cross section is 100, outer radius 160, radius to radius to the centroid 155, and then negative capital R 154.9462. Okay, negative F over 100 equals 248 megapascals. Now, if I have millimeters in newtons for the forces, or millimeters square for area, and you know this very well, then Newton and millimeters and megapascals make for a balanced equation. Okay, so before we solve for F, let's see what multiplies F on this part of the equation. And we have 154.9462, put this in the memory, minus 160 equals, and then divided by parentheses 155 minus close parentheses equals times 320 negative equals over 100 over 160. This is 1.8787 times F, and then here would be 100, that is 0.01 times F equals 248 megapascals. Okay, so F maximum, F limit, the answer to the problem is going to be negative 0.01 plus 1.8787 equals dividing 248. 1.8787 minus 0.1. Okay, and I have it 248 equals, take the inverse, so it's 132.7 newtons. This is the answer to the problem. Again, the limit case where yielding occurs, there's no or design factor is 1, and this is it. I'm going to stop recording.